Electrochemistry is a really interesting area of chemistry because it essentially adapts chemistry into almost every single technological object that we own. If it has a battery, it uses electrochemistry. So we will talk about those things, but it takes us a little while to get there. In the meantime, most programs cover electrochemistry differently in General Chemistry 1. So you may have gotten here without any background in electrochemistry at all. And for that reason, I want us to review what the rules of electrochemistry are according to oxidation number. And then we'll move forward to talk about how we talk about the rules in General Chemistry 2. So having both ways of describing this change will help you kind of understand what's going on. So I've also broken this first section up into two smaller parts. This first part, we're just going to look at individual particles, essentially, and what oxidation number means for those. And the second part, we will look at the oxidation numbers of molecules. So these are often referred to as oxidation reduction or reduction oxidation, or just redox for short. These reactions always involve a oxidation, which is defined as the loss of electrons, and the reduction, which is the gain of electrons. And these two things have to be side by side. Whenever something is oxidized, something else has to gain those electrons and be reduced. Now, most redox reactions have a chemical change that is occurring at the same time. So it's not just losing electrons, but it is also forming a new set of bonds, and it might be oxidized because of those new bonds, right? So those electrons, say if something bonds to oxygen, the oxygen pulls those electrons away to get them closer to the oxygen, and so therefore that atom is oxidized. Now, even though this is the more formal way of talking about oxidation and reduction, it does get a little confusing because electrons are negatively charged. The acronym Leo the Lion says GER is very helpful here. But in general, I'm going to talk about the oxidation state instead. I find that's a little bit easier to follow as we go through these reactions. The last thing I'll note is that when something is oxidized, it is often referred to as a reducing agent. It helps reduce the other thing. Or if something is reduced, it's often referred to as an oxidizing agent because it helps oxidize the other thing. I find that very confusing at this level. The books switch constantly back and forth between these two terms. I am, for the most part, going to ignore them and not use them. But just kind of keep that in mind if you see it as you're going through the book or going through the homework. So instead, we're going to use oxidation numbers to talk about these states. Oxidation numbers are kind of like charges. When we talk about ions, they are literally charges. But when it comes to compounds, they're not. It's just a way of describing how much electron density each atom will have at any point in time. So the number doesn't have like a literal meaning, but we have a way of just keeping track of how that exposure to electrons changes over time, and that gives us enough information. So when the oxidation number increases, it becomes more positive, we call this an oxidation, right? When that oxidation number decreases or becomes more negative, we call it a reduction. It's a literal reduction of positive charge. Now, of course, it's getting less positive because it has more electrons. Again, that gets confusing. Of course, if there's no change at all, the electrons are not moving. So usually I look at something and say, oh, it's more positive, therefore it's oxidized. If something decreases, then therefore it's a reduction. So when it comes to just atoms in their elemental form will always have an oxidation number of 0. So iron, sodium, xenon, helium, in their elemental state by themselves with no charge attached, we are just going to say there is 0. It's important to remember the 7 diatomic elements, H2, N2, O2, F2, Cl2, Br2, I2. This is the only way they show up, and this is their elemental form. So even though there's 2 of them, they still have an overall charge of 0, or oxidation number of 0. Now, if there is a charge on that atom, this is now an ion, and that ion is its oxidation number. So sodium ion, chloride ion, oxide ion, etc. This is also going to be true for simple salts as well. So NaCl is made up of positive and negative ions. Sodium still has a +1 oxidation state. Chlorine still has a -1. Or KBr, or magnesium oxide, right? Magnesium oxide, the magnesium is +2, the oxygen is -2. Again, if you're looking at salts, metal, then non-metal, almost always. So if we're looking at a chemical reaction, right? If you put copper wire into a silver ion solution, over time, the copper becomes an ion, it becomes the +2 ion, and the silver metal plates out. So we can see copper is going to +2. It's getting more positive, therefore it is oxidized. Silver, on the other hand, is getting less positive as it becomes a metal, right? We can see that in the formula. Therefore, we say the charge is getting smaller. It is being reduced. I only talk about Leo Ger afterwards because I think that's easier to follow. So now that we say, oh, copper's oxidized, therefore it's Leo. Silver is reduced, therefore it's Ger. All right, so look at each of these half reactions real quick and see if they're an oxidation or reduction. So tin going to tin 4+, it's more positive, so that's an oxidation. Iron +3 going to iron 2+, it's getting smaller on the number line scale, so it's a reduction. Chlorine gas going to chloride ion. Again, it's getting more negative on the number line scale. That is called a reduction. Finally, we have these reactions. In this case, magnesium is going to magnesium +2. More positives, that's an oxidation. Lead +4 is going to lead metal. That is a reduction, as it's getting less positive. So I said we'd cover compounds in the next video, but these products are all ionic compounds, which means we can really think of them as individual ions forming, right? So for these reactions, figure out the oxidation numbers of the elements on the left, figure out the oxidation numbers of the ions in each compound on the right, and then decide what is oxidized and what is reduced. Now, a key point for these reactions to consider is that the number of compounds you have doesn't make a difference, right? It doesn't matter if you have 1 MgO or 2 MgOs, the charges in those ionic complexes are the same no matter what. So we can basically ignore the coefficients of these compounds. So in both of these reactions, we're looking at elements reacting to form an ionic complex. Since sodium is by itself, and it has no charge listed, and it's a solid, all those things imply that this is sodium metal, which is a solid. So that has an oxidation state of 0. Same with chlorine gas, right? We don't typically see chlorine gas in general chemistry because it's extremely reactive, but nonetheless, Cl2 is by itself at 0. Right? It's only when they react with other compounds that they form an ionic complex. We get the sodium ion is a +1 and a chloride ion is a -1. Again, it doesn't matter how many sodium chlorides we have. Every sodium is always +1, every chloride is always -1. So we can see that change is going from 0 to +1, so that's an oxidation. Chlorine is going from 0 to -1, that is a reduction. This second reaction is a common reaction we see in general chemistry if you light magnesium on fire. Again, we have magnesium element, which is 0, oxygen element, which is 0, but we form the product magnesium oxide. Magnesium always forms +2 ions, oxygen always forms -2 ions. So these things are stuck together with equal and opposite charge, so we say magnesium goes from 0 to 2, so that is an oxidation. Oxygen goes from 0 to -2, that's a reduction. It's worth mentioning that it's not a surprise that both of these metals here got oxidized. Metals like to become oxidized. That's one of their key characteristics. And also, any reaction with oxygen is automatically going to make that compound become oxidized. So the term oxidized and the reactions of oxygen are both related.